Okay, let's get started with stress concentration fatigue loading. So this is the case where um, you have change in cross section. Remember, change in cross section leads to stress concentration. But what if the stresses were, what if the loads were fluctuating? How do you account for that? So clearly, just like stress concentration increases the stresses, uh, the dynamic part of the loading will actually lead to an increased stress, right? Because fluctuating loading is basically leads to more stress than what you'd get without with basically static loading. So what do you expect is a treatment which is very similar to that of static loading. So what we do here is we define stress concentration factors for fatigue loading, which are basically similar to the ones for static loading. So they are the ratio of the maximum stress divided by the nominal stress, just like before. Now there's something called notch sensitivity, which is how we'll connect the stress concentration factor in fatigue loading with the stress concentration factor in the static loading. This Q, and I'll show you how to compute Q, is defined as the ratio of Kf minus 1 divided by Kt minus 1. So there is a factor for bending and then the factor for shear. Okay. Okay, notch sensitivity. We'll get back how all this comes together in just a bit. Okay, so the key idea here is we need to compute the Kf and Kfs, just like we had to compute the Kt and Kts for static loading. The recipe to do that is here. First, we compute Kt, Kts using nominal stress in appendix A15. So this is something which we have done before for static loading. We know how to compute Kt and Kts. And remember that Kt and Kts are only are basically function of the geometry and not of the loading. So given the specimen diameters, dimensions, you can find Kt, Kts. The second step is to compute these factors Q, Qs. Now these factors, remember, are connecting Kt with Kf. And there are two ways of doing that, and I will show you those two ways. There's a plot and there's an analytical formula. And then once you get Q, if you want to find Kf, it's just these two formulas. This is just taking the earlier formula here and solving it for Kf as a function of Q and Kt. It is right here. Okay. Okay, so with that, let's see how to compute the notch sensitivity. There are two methods, as I said. First method is we have a figure which shows how Q varies as a function of the notch radius. So the notch radius is a function of the geometry. And these values here, which you see, are depend on the ultimate strength. So the ultimate strength is given in SI units, GPa, or they're given in kpsi for FPS. So depending on the ultimate strength and the notch radius, you can compute Q. So once you get Q and once you have KT, you can compute KF. This is the same thing for QS as a function of R. So this is the plot approach. The other approach is using analytical fit. So what they have done is they've taken these fits, these plots, and tried to use nonlinear regression to figure out what curve best explains these plots. Okay, so that is uh, these formulas. So for these formulas, there's a new constant called Newberg constant, which is needed. This Newberg constant appears in the equation as follows, as given here. Note that there is notch radius also in there, R, because ultimately you're fitting uh, Q as a function of R and this new constant called a Newberg constant. And this Newberg constant is actually a function of SUT. Okay, so it's basically, if you look at this plot, it is Q is a function of SUT and R, and that's pretty much what is showing up in these equations. So they look pretty complicated, but really they are, once you program them in some software, it's just a matter of plugging in the values and evaluating it. Okay, so there are different factors for bending or axial, and then there's a one for torsion. So this is Q, and this is clearly QS, right? Okay, so what we'll do is we'll see how to apply this. Okay, a steel shaft in bending has an ultimate strength of 690, so S, UT 690 megapascals, and a shoulder with a fillet of radius 3 millimeters. So this again connecting a 32 mm diameter with 38. This is a figure we've seen before, something like this. This is 32. The larger one is 38. Note that there is, if this is 30, this is 38, this radius has to be what? 3, right? 3 and 3 here. So 3 plus 3 plus 32 is going to be 38. And that's precisely what you see here. Estimate KF using figure and equations. Okay. So we'll basically use essentially this recipe to compute KF and KFS. Uh, 1, 2, and 3. So first is compute KT. So let's do that. First step, compute KT. Okay, this is not a shear problem, it's just a bending problem. So you don't will have to worry about QS or KTS or KFS. So let's compute KT. Now for that we need to look at, I just picked this figure from the appendix 15.9 because this is the exactly the specimen shown here. Right? This specimen is exactly what it is here. So the outer diameter is 38, the inner diameter is 32, and then the radius is 3. So what we need to compute KT is D, uppercase D divided by lowercase d. So it's 38 divided by 32 comes out to be 1.1875. And then we need, I think, the radius divided by the lowercase d. So that's 3 divided by 32 comes out to be 0.093, no, 0.9375, my bad. 0.9375. Uh, and just for practical purpose, I'm just going to round this to, well, we have 1.1 here. So why did I round it to 1.1 and make my life easy when I try to find KT? And then this, I'm going to round to, well, zero point 0.1 is closest, so 0.1. So now with that, I'm looking at 0.1 and I'm looking at 1.1, 1.1. So that 1.1 is this curve. So I need to look at this point, this point. Okay, so it seems like it's exactly here, 1.6. So KT is 1.6. So from all this, KT is 1.6. Okay, that completes the first step, computing KT. Now we need to compute Q, in this case, not QS, just Q, because bending. So we can look at the plot. Let's look at the plot. Here we have to look at the plot of Q, not QS. The ultimate strength in this case is 690 megapascals. Okay, now the issue is that you have in gigapascals. So 690 megapascals is also equal to 0.69 gigapascal, right? Or I think the closest one is zero point 0.7. So let's just round to 0.7 gigapascal. So we're looking at 0.7 gigapascal. And then we have a notch radius. So the thing is, the radius here is in inches, if you can see it. And then the radius here is in mm. And I think we want 32 mm. Oh, sorry, 3 mm. So R is 3 mm. Okay, so if R is 3 mm, then 3 mm is here, and then SUT is here. So it looks like we are looking at this point, exactly this point. That seems like This is 0.9. So it's between zero point 0.8 and zero point 0.9. I would just go with 0.85. So let me erase this. This looks like it is sitting right at 0.85. So Q is 0.85. What I did to get this was I looked at 3 mm, which is here, and then I looked at 7 GPa, which is here, and I ended up with this Q. So 0.85. So the second part of the problem, B or 2, is Q is 0.85 from plot. Okay, the other way to find uh, is through using this fit. Okay, so Q is 1 plus, so this formula, R will be 3. Square root of A would depend on the loading. So we are looking at bending. So we have to use one of these two. In this case, X, this is SI, this is FPS, this is SI units. So we need to look at SI units. The SUT is 690 megapascals. So this fits within the range described here. So we need to use this formula. Okay, so I'm going to take this formula, write it down, and put SUT as 690 megapascals. Okay, so square root of A is 1.24 minus 2.25 10 raised to negative 3 SUT plus 1.6 times 10 raised to negative 6 SUT square. And to continue to next line, minus 4.11 10 raised to negative 10 SUT cube, and SUT is 690 megapascals. Okay, so putting in this value, we get A, square root of A is 0.314 mm raised to half, because it's square root of A. A has a dimension of mm, and then Q is 1 plus square root of 1 plus 1 divided by 1 plus square root of A divided by square root of R. So 1 plus 1 plus square root of A is already given. So it's 0.31. Square root of R is going to be square root of 3. Comes out to be 0.8465. Okay, so you can see uh, its value is probably very close. So this is what I got from the plot. And then Q 0.8465 from curve fit. So they are indeed very close. 0.85 versus 0.8465. Okay, so the final step is compute. Third step is to compute KF. So we know that KF is 1 plus Q, KT minus 1. So we can use plot. So in this case, we'll use Q equals 0.85. KT is 1.6. We computed in the first step. So using this value of Q, we get KF equals 1.425. And then if you use the curve fit, Q you'll use as 8465. From that, you get KF equals 1.4, 1.423. 1.423. So this is the answer to the first part, A, using the plot. This is the answer to the second part using the fit. And you see that the answers are pretty close to each other, okay, almost identical to the first two decimal places. Now we'll push this a step further and do the next problem, which is uh, a full-blown problem for stress concentration under fatigue loading. So let's read through. Figure 622A shows a rotating shaft simply supported in ball bearings at A and D. So the way to show ball bearing is usually a pin joint, hinge joint like this, and loaded by a non-rotating force F. F is 6.8, so it looks like the force is here, 6.8 kilonewtons. Using ASTM minimum strength, estimate the life of the part. Now, ASTM strength, this is something which you need a table, you need like a look up the handbook to figure out what the minimum strength is. This is basically a way to compute SUT. So I figured out that SUT for this particular shaft is for AISI 1050 is actually 690 megapascals, and I'll give this to you. Okay, but otherwise you can get it from a handbook. So we want to estimate the life of the part. And the life of the part is given by n. So this is at hinting that you have to somehow use the formula SF equals A n raised to B. Now remember that this formula is only valid from 10 raised to 3 to 10 raised to 6. So after doing this problem, you figure out that n is less than 1000 or greater than 1 million, then your calculations are incorrect and you'll have to find another way of computing um, you'll have to find another way of computing n, right? This formula is only valid for this range. So be mindful of that when you solve any problem. This is just our hunch that the life is usually between 1000 and a million. Okay, and then we can go back and I can talk a little bit about if n was what would happen if n was greater than a million or less than 1000. Okay, so this is the assumption. So if we are going with this assumption, the question is what is A and B equal to? Well, A is something we wrote down in the last class. It was F times SUT divided by SE, and this is actually squared. And it also depends on, well, the B is 1/3 log to the base 10 SE divided by F SUT. And so it's clear that in order to solve this problem, we need to estimate, we need to compute uh, A and B, obviously. So let me put it this way. N is unknown. What we need to compute is SE, F, SUT, and SF. Okay. Now it turns out that SUT is given. It's right here. It's given to us. So what remains is SEF and SF. Okay. So how do we compute that? Well, for SE, we have what we did this last time. We had a whole entire section devoted to computing SE, right? So this is something which we can look at. I think it was the last lecture was 16. So see, I think it's 16 and 15. So two sections. This is 17. So 15 or 16. This was exclusively, I think. Well, let me use this different color here. This was sure 15, 16, and then this was 15. And actually, let me pull that up. Okay, so 16 was endurance limit when there are all these factors, right? And then 15 is basically giving you how to compute F. And it's also letting you compute SE prime. What is SE prime? SE prime is the endurance of a lab specimen, right? So this experiment, if you do the experiment, the fatigue experiment in the lab, you'll get SE prime, and then you need to go through all these factors to compute SE. So what I guess I could write here is this depends on uh, F and SE prime. So once you have these two from 15, you can then compute. Uh, so this should be lecture 16. And so that's for 15. And then the new element here is SF, which is very unique to this problem. And I'll get to that in just a bit. So this one comes from, actually, this is the load appearing on the shaft. This load will be from actually this figure. So this is the load coming from the shaft, because once you know the load, you can estimate the life. So there are multiple things in this problem. We'll divide into two steps. One is we'll compute SE first, and everything associated with it, and then we'll compute SF. Okay, and that will make it slightly easier to go along. So first, so one, we'll compute SE prime F and consequently SE. And the second step, we'll compute SF. And then finally, we'll use this formula SF equals A n raised to B to compute N. Okay, so this is our methodology. So let's see how to compute the first step. Okay, now if you go back to the problem, you'll see that uh, SE is not given to you. So SE is not given to you, but we know that SE can be found. If you go back here, you can see that SE, there is a formula which depends on SUT. So if SUT is less than 200 kpsi, sorry, this is SI unit, right? You're given 690 megapascals. So SUT is 690, which is less than 1400. So SE prime is 0.5 SUT. So that's easy. So we have SE equals 0.5 SUT, and this is coming from, uh, it was lecture 15, this one. And so what is that? That's 0.5 times 690 megapascals. And so SE equals 345 megapascals. And this should actually be SE prime. Okay, so that's SE prime. Now, I've got this. Let's move on to compute um, other things. How about we compute SE? Okay, since we had already computed SE prime. So for SE prime, we have these factors which modify the endurance. They are K, KB, KC, KD, and KE, surface factor, size factor, load factor, and so on. What we'll try to do is try to see in the language of the problem if we can find a surface factor. What is a surface factor? It basically is related to the surface finish. So going back to this problem, we try to, wasn't it, it's 6.8 in the problem? There is a question. What is 6.8? Okay, I'm sort of lost on the question in the, okay, no problem. Okay, 6.8 is just a force. Okay, the force is, I see, I might know what the problem is. I think you might have confused F with SF. SF is, um, in this case, SF is not, let's see, SF, we can go back and see the units of SF. That's what is important. I think the confusion is SF the same as F? Okay, if you go back to 15. So what's going on here is we have a bending load, right? So we have talking of sigma, and then we get the SN curve. So where did we get this? We got it from uh, some kind of a bending load, which is right here. So this formula SN curve is actually a fatigue strike in bending. This is some moment. So if it's moment, it is not F. F is 6.8. So we want to find the moment. So SF is actually related to this diagram. And I should have been, it's my fault, I should have been more clear about it. SF is related to uh, related to M. Okay, so we need to find where M is. So the question, oh, okay, where the SUT came from? Yeah, SUT came from uh, Yeah, SUT came from minimum. So it's some handbook. But I think you, because you said this, I think I made this very clear. But thanks for the question, because SF will come from the maximum moment, because that was what will show up here, and that's what is was used in the derivation. In fact, uh, it is actually, see, you see this, it's basically a stress right here. It's basically a stress. So what we need to do is, in this case, we need to compute SF would be my divided by I, okay, because this is sigma. And this m, what we're interested in here is the maximum m. I just put m here, but we would have to figure out what that maximum is. Is it, clearly looks like m max is the one, but you'll see that it may not be m max, it might be something else, depending on the stress concentration, because that's what we're talking about. So we'll get to it when we'll get to it later on. Let's continue with um this part. So we got SE prime, let's compute SE. It is Ka, Kb, Kc, Kd, Ke, Se prime. Okay. Now, first thing is, what is the first factor? It's a surface finish. So ground, hot rolled, forged, and so on. So what is there in the language here which hints at that? So we have, okay, shafts, cold drawn steel. Yeah, cold drawn is the keyword. So for cold drawn steel, we have machined or cold drawn. So we'll use this. So here A equals, and we need to go for megapascals because the SUT is in megapascals. So A is 3.04 and B is minus 0.217. Do not confuse this with the other A and B in the formula SF equals A times n raised to B. Okay, so Ka equals A times SUT raised to B, 3.04, 690 raised to minus 0.217. So Ka is comes out to 0.714. That's one. Next, let's check the next factor. Next factor is the size factor, which basically depends on, well, it depends on rotating or non-rotating, and it depends on the loading. Okay, so in this case, if you go back to the problem, we will see that, so we see the keyword rotating. There's a rotating shaft, and then we also see that it's subject to a bending moment. So it's rotating and it is bending. So we need to go with uh, rotating and bending. So we'll have to use these formulas. Okay, so we'll use 1.25 times d raised to minus 0.107 because we are looking at SI units and not FPS. The dimensions are in SI units. So for next part, um, we have rotating, bending. So the formula is Kb equals 1.24 d raised to minus 0.107. Okay, Kb equals 1.24, and I think we've done this in the previous class. Just happens that uh, we can, well, we have 32, 38, 35. So what you can do is, uh, it seems like the maximum stress will occur. Actually, we did this. We found that the larger the diameter, the more is Kb. I think we, was it here? Let's see if it was here. Yeah. So what we did was, for exactly the same dimensions, 32 and 38, we computed Kb. We used 32, we got 0.855. If we used uh, 38, which I think was here, I used 38, and I found it was 0.84. So the smaller the k is, the more conservative it is, and the larger the k is, the less conservative it is, because remember it's kb times the c prime. I would just be less conservative. Let's just use 0.855. Really, I don't think the answers will change by a whole lot if we use either of them. Let's be less conservative, use 0.855 like we've done before. So kb is 32 times 0.107, and I would cross-reference this with lecture 16. Okay, so using this, we have kb equals 0.86. So 855, I rounded to 86. 855 is equal to 0.86. Okay, so that's B. Let's look at KC. So go back to here, I think, K load factor. So this depends on bending axial torsion. Super easy. The loading is bending, so Kc is 1. Uh, Kc equals 1 because this is bending. Okay, next. Next we have AD. AD depends on temperature. Let's see if there's any wording about temperature. If it says anything about the shaft having being loaded in the different temperature conditions, but it doesn't look like there's anything about temperature. So KD is going to be 1 because there's no temperature effect. It's assumed to be at room temperature. And the last factor is the reliability factor. There's no mention of reliability here, so we'll assume KD and KE equals 1 in the absence of those factors. So KD equals KE equals 1. Okay, so we are set now to compute SE. SE is Ka, Kb, Kc, Kd, Ke, Se prime. Ka was 0.714, Kb is 0.86, Kd, K, Ckd, Ke is 1, Se prime is 345, and so we get S equals 220 megapascals. Okay, now let's move on to computing F. So we've got SEF is what remains is F, and let's see what F depends on. F is should be here. F SUT curve. This is the easier one. So this depends on SUT only, and SUT is 690 megapascals. Now this is 600, 600. This is 700. So it's probably I would say maybe this is 700. So it's very close to 700, somewhere here. Okay, this region somewhere. Uh, to be very accurate, maybe it's over here. What I'll do is I'll just round it to 0.84. Okay. So if you write something between, I guess, 0.84 and 85, it should be okay. I'm just going to round it to 0.84. Okay, so from F SUT curve, which was lecture, I think 15, F is approximately equal to 0.84. Okay, I think we are pretty much done with all these. Okay, now let's compute SF. Okay, SF comes from the loading. It actually is SF is my divided by I equals sigma. So what you'll do is you'll compute the maximum moment, right? Because maximum moment means maximum S, and the lower the life. I is going to be, well, it depends on the cross section, so on, and y is basically the distance from the neutral axis. The part which is most highly stressed is the top and bottom surface. It doesn't really, you don't have to worry about compression or tension. Use the maximum value. In this case, it's symmetric, so it doesn't really matter if it's top or bottom. You're just going to use the absolute value. Now, it turns out that they have already drawn the moment diagram. They have not indicated what the scale is, but they have drawn it. So what we will see is that there are 2 points where the stress is maximum. There is, sorry, 1 point where the stress is maximum, M max, right? Let's try to see if we can compute that M max. What I'm going to do is I will assume this to be a beam and then draw the free body diagram with 6.8 kilonewton force, compute R1, R2 through free body diagram, then draw the shear force diagram, and then draw the bending moment diagram. The shear force diagram will help you to compute the bending moment diagram. So let's proceed in the step-by-step fashion to compute the maximum moment. So part 2, compute SF. This is the max bending moment. Okay, and what I'll do is I'll draw a free body diagram. The shaft has 250 plus 75, that's 325, and then 100 plus 25 is 225. So the force is 325 from the left side and 225 from the right side. R1, R2, let's put it here, 6.8 kilonewton. This is 325 millimeters and 225 millimeters. Okay, so X, Y, summation of forces is 0. That would give me R1 plus R2 minus 6.8 equals 0. And then moment about, let's call this is point A, that's A, B, okay, A and D. Actually, A and D. So A, D. So let's take moment about A equals 0. So 6.8 times 325, that would be a clockwise moment. So I'll put negative sign because I'll turn the whole beam in the clockwise direction. And then we have plus R2 times 325 plus 225 is the total distance from A. Okay, so if you compute R2, you would get 4.02 kilonewtons and R1 equals 2.78 kilonewtons. Okay, now what we need to do is we need to compute uh, the moment. Okay, so now I could draw the shear force diagram, but I think there's a shorter way to do this. We can actually find the moment at here without actually doing the shear force diagram because it's not asked. So what we can do is essentially you'll draw the free body diagram of this, assuming a cut right at uh, the point of application of this, well, right at B, or in this case, if you want to find the moment at B, or at the application of 6.8 kilonewton force, and that pretty much will give you the moment. So this is how you'll do it. So M, so I'm going to try to attempt to compute M max, okay, first. So I'll draw the beam. This force is now R1, 2.78. This distance is nothing but 325. And then we want to find M max. Right? There's no force between A and 6.8. So that would be the free body diagram. So M max is 2.78 kilonewtons, so 10 raised to 3, and 325 millimeters. So when you convert millimeters to meters and kilonewtons to newtons, you just end up doing 0.3 to 0.325. Right? What I did was I eliminated kilonewtons with millimeters. So 1000 cancels with the 1 e negative 3 for millimeters. So M max comes out to be 903.5. Okay. Oh, I kept it in, sorry, I just, the units really don't matter unless you are, we'll just keep it in millimeters. So it'll be 0.903, I think. Yeah. Okay. Now, so let's call this point, I think they give a name for this. I mean, let's just call this, just for identification, let's call this point E. E. Okay, because I don't want to say M max is sigma max, because the sigma max actually is something we need to find. Sigma max really depends. So you think that sigma max will be at the location where M max occur, but in this case that may not be true because there is a stress concentration here, and the stress concentration is the effect of increasing the stress. So even though the stress at MB is not, the moment at MB is less than the moment at E, the stress could be higher because of the stress concentration factor. So let me write the stress at E. This is the normal bending stress at E. So sigma, this is point E. Sigma E is M max Y divided by I. So it will be 0.903. Move this around. That's the max. Y is the distance from neutral axis to the top. The diameter here is 38, right? 38 mm. 38 times, you know what, let me write the formula down here actually first. M max Y is D divided by 2, and I is pi D raised to 4 divided by 64. So it comes out to be 32 pi D cube times M max. Okay, now it's easier. So this is 32 times 0.903 divided by pi times 0.038 cube, because I converted millimeters to meters. Okay, so this gives me sigma E is 167 megapascals. Okay, so that's the stress at E. Now let's compute stress at B, because we suspect that there's a stress concentration due to which this MB is going to be amplified. So let's compute stress at B. First, we need to find a moment at B. So we want a moment at a distance of 250 from A. So beam 2.78 kilonewtons. Uh, Here we would have MB, and this distance is 250 millimeters. So MB is going to be 2.78 kilonewtons times 250. So I convert 250 to meters. So 0.25. So that comes out to be 695 Newton meters. Okay, next we compute the stress at B. The same formula, M B Y divided by I. So you'll get a similar answer. It will be 32 MB divided by pi d cube. However, mind you, the d is different here. The d is actually the diameter of the smaller shaft, 32. Remember, you could, at this point, you could use 32 or you could use 38. The reason why you use 32 is because the smaller the diameter, higher the stress. So between the two, on the left side, you have a higher stress. So let's use that one. So we have 32 times 695. It's zero point 0.6 kilo. I think it's 6.95. Let me check this. 2.78. Yeah, it's 0.69, 0.695. My bad here. 695. So 0.695 pi times 0.032 cube. Okay, so sigma b will come out to be 216 megapascals. Okay, now what we can see is stress at E is 167 and stress at B is 216. So why did this happen? Well, it happened because uh, even though the moment here is greater than the moment at B, the shaft diameter at E is greater than the shaft diameter at B. And because of that, because of the effect of D, this D, which is 0.032 versus 0.038, we found that without any stress concentration, the stress at B is greater than stress at A. So, so that's that. However, the stress at B is actually much higher than 216, and that's because of stress concentration factor. So what we'll do is we'll next find Kf, compute Kf at B. Why? Because here we see that there's a change in geometry. So the geometry changes from 30 to 38. Turns out that we've already solved this problem. We've solved this problem where the geometry changes from 38 to 32. We found from last class that the stress concentration factor Kf is about 1.42 or 1.425, 1.423 using different methods. They're almost the same. Let's just stick with 4 to 5, let's say. Okay, so from question 1, from Q1, this very same lecture, we have Kf is 1.425. That means sigma at B, or what we'll write, that's going to be our SB. SF is going to be Kf times sigma at B. So 1.425 times 216. So SF comes out to be 308. You know what, let me put a B here just to show that B is the maximum stress. It is 308 megapascals. Okay, so what we've done so far is we have now computed SFB. This is the maximum load which appears, and it appears at B. So to summarize, we have computed SF. Now we'll use this formula SF equals A n raised to B to compute N. Okay, so what is A? A is FSUT squared divided by SC. So luckily we have all this computed previously. If you go here, we have SE, maybe here. F is 0.84, SE is 220. Can SUT is 690 megapascals. So we have everything here. 0.84, SUT is 690 divided by SE, which is 220. This comes out to be 1564 megapascals. And then B is 1/3 log to the base 10 SC divided by F times SUT, 1/3 log to the base 10. SE is 220, F is 0.84, and SUT is 690. So B comes out to be minus 0.142. Okay, the final step is SF at B equals A n raised to B. SF is known, it is, or you know what, let's just simplify this. N equals SF at B divided by A raised to 1 divided by B. So SF is 308, where it came from here, 308. A is 1564. B is minus 0.142. And from this, we can get N equals, so it's approximation. I rounded it up to 94,000 cycles. Okay, so we have to check if N is between 1000 and 10 raised to 6. We see that this is, what is this? This is 9.4 times 10 raised to 4, 10 raised to 4. Yeah, or if you want to round it up, this is like 10, so it's 10 raised to 5. So it's 10 raised to 5, and so 10 raised to 5 is in between 1000 and 10 raised to 6, so it checks out, and we know that our assumption was right. Now, question: what would happen? What would make you change this assumption? Let's say in this calculation, if you found out that SF, now SF is 308. Okay, uh, if you found out that SF was less than SE, let's look at SE. SE is SE is, where did I put it? Here maybe. Yeah, SE. So if SF was less than 220 MPa, then it's infinite life, right? However, if SF was less than 220 MPa, then you'll not even do the calculation for computing n. You'll just write uh, n equals to 10 raised to 6, or you can say infinite life. N is infinity, infinite life. Okay, so do not do any calculation in that case. The moment you get SE is less than SF, SF is less than SE, immediately you know it's infinite life. If you find that n comes out to be less than 1000 though, now there is a problem because we have not really developed a formula for what happens when n is less than. So if you get the SN curve, which is right here, so we've developed the formula for this yellow region. We have not developed a formula for this region. Okay, what I would do is, instead of trying to spend my time figuring out the exact value for n is in that case, that is, if you find that either you find n is less than 1000, or you find that the load, that is uh, SF is between SUT and FSUT, then you know for sure it's going to be between 0 and 1000. In that case, I wouldn't even bother doing the calculation. I would say that this is going to fail sort of very soon, and so there's no real point of finding the exact cycle. Does it really, in other words, having something fail at 1 cycle or 10 cycles or 100 cycles is nothing, right? Because if something spins fast, it'll probably complete 100 cycles in no time. So really, you can just say it's less than 1000 and you stop there. You don't really compute. It is 9.44. It doesn't really matter. So it's because the cycles are so few to failure that you just say it's going to fail within 1000 cycles and you just don't bother. So then what I'm going to write here is, um, so this is case one case. Another case is if SF was between FSUT if SF was between FSUT and SUT, right? Because that's the region, that's the band where you have uh, low cycle and finite life. I would just say n is less than 1000 and stop there. Okay. And I would really ask you to compute exact value because it's small enough. Okay, so that shows you how to um, do the fatigue calculations for something which is just, I would say this is a more complete example which shows you the entire design cycle starting from stresses and unknown endurance and so on.